Hello everyone. Once again, I'll be speaking about the air flushing technology, but in this particular segment, I'll be speaking about a pilot scale experiment that we performed at CFB BORDEN that looked at soil vacuum extraction. In the next segment, I'll be speaking about in situ air sparging. This particular experiment was an investigation into soil vacuum extraction of a dense non-aqueous phase liquid source that was released within a sheet piled wall cell at CFB BORDEN. If you're interested in the glorious details about this, it can be found in a groundwater paper. The general objectives of this experiment were to assess the ability of conventional soil vapor extraction technology to remove a known mass of a dense non-aqueous phase liquid, to develop monitoring techniques that might be used, to explore the SVE operational procedures, and finally to detail the role of the capillary fringe in the mass removal of an SVE system. So the cell we used is a 9 by 9 meter cell. Again, it's a hydraulically isolated block of BORDEN aquifer. It contains approximately 3.3 meters deep of spatially variable sand, and it was enclosed in two sealable sheet pile walls. The DNAPL source was released under a constant head. Approximately 770 liters of PCE were released over a 70-hour time frame. The water table was approximately 15 centimeters below ground surface at the time. Here's a cross-section from some work by Thomson of the permeability field of BORDEN material. You can see that the darker colors indicate a lower hydraulic conductivity. So BORDEN sand is a very layered sand with variations on the centimeter scale. After the DNAPL source was released, some geophysical work was done to map the source, and the understanding of the source approximately 570 hours after a release looked something like was on this slide. Some pools of sample that were elevated about 0.5 to 0.75 meters below ground surface, and then some deeper down, approximately 3.3, or on the actual bottom of the sand at the clay sand interface. When we arrived at the cell, the source was in place, and our effort here was attempting to use conventional soil vapor extraction to see how much mass we could remove from the cell. So our system consisted of 6 extraction wells. All of the extraction wells were connected to a central header that ran to the extraction system on the left. Also, within the aquifer, we installed a series of soil gas probes so that we could monitor both pressure and soil gas concentrations. Here's a picture of the soil gas pressure at 2 meters below the ground surface, clearly showing that you have a flow at that depth and a substantial pressure at that depth to propagate the flow from left to right. We operated the SVE system for approximately 550 days. Here's a plot of the flow rate versus time, and we played around with the flow rate. Started off at a very high flow rate, approximately 1,000 meters cubed per day, dropped the rate down, and then increased it again, and generally tried to optimize the mass extraction from this system over, as I said, over approximately 500 days. The symbols A, B, C, D, E, and F are soil gas sampling time frames where we actually shut off the SVE system so we would be able to sample soil gas in an aquifer that was back to equilibrium. Here's a view of the off-gas concentration profile versus log time. Again, the A, B, C, D, and E indicating those times when the system was shut off and then turned back on. So the A, B, and C, and D indicates elevated off-gas concentrations that reflecting more mass had been able to transfer from the aqueous phase into the gas phase. On this plot I have stage 1, stage 2, stage 3. Stage 1, which lasts for approximately 10 days, we've called the equilibrium stage. That's the stage where the concentration is the highest and sustained. Stage 2 is the transition stage where the off-gas concentration goes from the higher, more equilibrium-based concentration to the long stage 3, the tailing stage. Stage 2 lasts for approximately 20 days, and then the entire system stayed within stage 3 for the entire duration of the experiment. If we take the off-gas concentration profiles and we take the flow rate profiles and we multiply them in a very simple way, we can then estimate the cumulative mass extracted over the entire SVE operation. And for this case, you can see very quickly after approximately 50 days, the system reached a point of asymptotic mass recovery, and over the entire experimental period, we recovered approximately 63% of the mass that we estimated we would be able to recover. So what we saw was what most sites see as a typical soil vacuum extraction profile, where the concentration starts off high at an equilibrium point, follows through a transition stage to a long tail, and that's reflected in the mass removal profile, which has a steady increase early on and then this late time asymptotic tailing. When we went in and took soil cores to try and understand exactly what was happening within the profile, here's a result of one soil core. On the right-hand side is the moisture content, and on the left-hand side is the soil concentration profile. You can see an image of a soil core on the left here that correlates to a very high concentration of TCE within the soil. On the right-hand side is the moisture content profile, and you can see it's somewhat unsaturated until about a depth of 2, and then down below here, this would be the capillary fringe. As I said, it's a clay zone approximately 3.3 meters down. So the system that we had for a dense non-aqueous phase liquid is one where we have airflow above and below a lower permeability lens. In our case, we had a dense non-aqueous phase liquid that would sit on the lower permeability lens or high capillary pressure barrier, and above that we would have aqueous phase that would also pool there. So the mass transfer then from the entrapped or pooled DNAPL in that interface would have to first dissolve, then it would have to diffuse across the high moisture content zone into a mobile pathway that we had air that was sweeping across. So that's a glimpse at one pilot scale experiment in which we try to show that the use of an SVE, while it could remove some mass, did have problems dealing with mass removal from a dense non-aqueous phase case. In the next segment, I'll be speaking about a pilot scale study where we looked at the performance of in situ air sparging. That's all for now. Enjoy.